Lesson 1.7 is on rational numbers. Rational numbers. And before we get into that, does anyone know what other name we have for rational numbers?
Fraction.
It's a fraction. Okay, a rational number is a fraction where the numerator and denominator are both whole numbers. Okay. The first activity for you there you're going to do on your own, or at least try your best. I would do it in pencil, or don't write anything. Just try it in your head. But you're taking the words rational number, whole number, real number, natural number, integers, and irrational numbers, and you're going to fill in the diagram. And then we will give examples for each category as well. So take 30 seconds to think about that, and then I'll do it on the board. All right, folks, two different ways to do this. You can start with the biggest group of numbers and work down, or you can start with the smallest group of numbers and work up. We have already done this part of the chart in Unit 1. Who knows what the smallest little box is called?
Natural.
Natural numbers. Can you give us an example?
1, 2, 3.
Yeah, it starts at 1 and it just is our counting numbers up. Good. One group bigger than the natural numbers, so the group that includes the natural numbers and something else is called?
Whole numbers.
Whole numbers.
Welcome back.
And you can use a little hashtag for numbers in your little boxes. And what's the difference between whole numbers and natural numbers?
Whole numbers include 0.
Includes 0. So we've got 0, 1, 2, ... In our next group, which includes all the whole numbers and some more.
What? Oh, never mind.
Real numbers? Integers?
Integers. Makes sense. That's what we were working with in the first half of Unit 1. So we've got our integers, which includes?
Negative and positive.
So we've got -3. Oh, we should add that little ... in front to know that we go all the way to negative infinity. We cross 0 and keep counting. My list is really ugly. You probably don't want to write it quite that ugly. And the next group of numbers, give you a hint. We studied integers, now we're studying rational numbers. And we did take a note on rational numbers at the beginning of Unit 1. We said it's any number that can be expressed as a fraction where the numerator and the denominator are both whole numbers. So it's any value that can be expressed as a fraction using whole numbers. So that's things like 1/2 or -7/4. Or what about 2.5? That could be expressed as a fraction, right? 5/2 is the same as 2.5. What about this one? -0.3 with a bar over it. What does that mean?
That means it's repeating.
It's a repeating decimal. Can it be expressed as a fraction using whole numbers? Exactly.
No.
Well, I wrote it in the rational number box, so I hope it can be.
Over 100.
Erase it.
Can you put it over 10 or over 100?
You could, as long as you can express it as a fraction using whole numbers, then it's a rational number. Give you a hint. This is the same as, it's not a hint, it's the answer. It's -1/3.
Oh, 33.332.
Mm-hmm.
Kaboom.
Okay. Let's carry on. If these are the rational numbers, then what's this group? Irrational. Irrational. These are any numbers that can't be expressed as a fraction using whole numbers. So for instance, square root of 2 or pi, right? 3.14, yada, yada, yada. It's a never-ending, never repeating, never terminating, never repeating decimal. Not very many. I used to know more. Square root of 5 is in there. It's an ongoing decimal. There are other special numbers like the number e, which you don't know.
What's the number?
It's an irrational number.
Cool.
Okay. What do all these numbers fit into?
Fraction.
Numbers.
What's the biggest category? The only word you have left.
Real numbers.
These are all real numbers. Okay, that means they really exist somewhere on the number line.
Even E?
Even E. Okay? I does not exist, though. I is an imaginary number, not a real number. Okay?
That's a letter, actually. You're getting your alphabet.
That's okay. So this box that we just drew is all the numbers. Positive,
What is it?
negative, as well as all the fractions. And all the decimals that fit in between here. They're all included in this diagram. So, nice. So, your little sentence there. Rational numbers are the group of numbers that include 0 and any positive and negative number
Whole number. Huh?
that can be expressed as a fraction using whole numbers. So what that means is we could have any number, and I'm going to use letters to represent my numbers, but you could have A over B. The whole thing itself does not have to be a whole number. It can be a decimal as long as it's terminating or repeating. It can be a fraction. But each of these parts, A and B, they both have to be whole numbers. Okay? But the fraction itself doesn't have to reduce to a whole number. So on a number line, we can see that the set of rational numbers includes the integers and a lot of the numbers in between. Okay? So you can see that number line, we split up between 1 and 2. I split it into fifths just to show that, 1 and 1/5 is in there and 1 and 3/5 is in there. Between 2 and 3, I split it into thirds. Those also count. 2 and 2/3. That's a rational number. The next one is split into fourths. So any way you want to split it, it's going to work because it can be expressed as a fraction using whole numbers. So any one of those places in between is included in the set of rational numbers. Now, when we're working with rational numbers, we're working with fractions and division and things like that, so it's really important that we get our terminology. Do you guys know what the parts of a division sentence are called?
I forget.
Denominator
There's a numerator and a denominator. Do you know what the answer to a division is called? A quotient. Okay, there's some terminology that you're going to need. Okay? Going to need to be able to use that. And looking up to the top of page 5, we continue our notes. And it tells us that rational numbers, and this is going to make sense later, we're going to practice this as we go. Rational numbers are helpful because they allow us to express any value in an alternate form. Sometimes we're looking for simplest form, but sometimes we just need that number written a different way. So we can do that using rational numbers. This means that we can write the same number in a different way. Let's go ahead and look at a few examples there. I've written a handful of examples, and your goal is to rewrite each of those numbers in 3 equivalent forms. So I'll do the first one with you from your suggestions. We're starting with 1/2. How can I write that in an equivalent form? Yeah, we could do that. That's right. That would definitely be an equivalent form. That's going from decimal to fraction, fraction to decimal. What we want to do here is use different whole numbers in the fraction.
2/4.
So it could be 2/4.
5/10.
Could be 5/10. One more. 25 over 50. All right, go ahead and do the same thing for B, C, and D. Maybe first I should ask, how did we get from this form to the next form? What did we do?
We
just
double
times
it.
it by
times
2.
the top
So
by 2, and then you do also the bottom.
good. As long as we take the numerator and we multiply it and the denominator and multiply it by the same number, we should be good to go. Okay? From here to here, we multiply the numerator and the denominator by 5.
Or like 5 and 6.
So go ahead and try B, C, and D. B might look a little bit tricky at first because you just have a whole number there, the number 6, and we need to represent it as a fraction, as a rational number. Well, if you remember back, you might know that 6 is the same as 6 over 1. It just means 6 wholes. You have some whole that you've split into, you haven't split at all, it's just one big part, and you have 6 of them. From here, it's a little bit easier to get other equivalent forms, because now we recognize that we can write it as a fraction with a numerator and a denominator. And again, in order to get an equivalent equation, an equivalent form for this value, we just need to multiply the denominator and the numerator by the same value, and it really doesn't matter what that value is. We could do it by 3, as long as they are both by 3. And then we've come up with 18 over 3. And we can double check that that's an equivalent form because 18 divided by 3 is indeed 6. Go ahead and try to get at least one other equivalent form for B, and then we'll move on to C. In C, we have the rational number 6 over 3. We know that 6 over 3 can also be read 6 divided by 3, which is just 2. So one equivalent form is just 2. Now we could go back into rational form, into fractions, in order to get our other equivalent forms, a few more. And again, we're just taking the top and bottom number, multiplying them by the same value. So we could have something like 12 over 6. And each time we can kind of double check in our head that yes, indeed 12 divided by 6 is 2. Try and get a couple more there, and then we'll move on. And also try to get 3 equivalent forms for D, which is 11 over 15. Now it's great to be able to express any number in an equivalent format using fractions. It can be very helpful, but when we're using rational numbers in math, or when we're finding a solution to a problem, we want to be able to express that rational number in lowest terms. We always want to be able to get into lowest terms. So in A here, we have this fraction, 4 over 8, but we want to express it in lowest terms. Now you might right away know, okay, I can reduce this to 1 over 2, because 4/8 is 1/2. If I had a chocolate bar with 8 pieces and I ate 4 of them, I would have eaten half of the chocolate bar. Or we could divide the numerator and the denominator by 4. And then I'll get 4 divided by 4 is 1, 8 divided by 4 is 2. Another way to think about it is using this picture that I've drawn. And in the top row, you can see that the bar is split into 8 pieces, and I've highlighted 4 of them because we have 4/8. Now in the bottom row, I've taken the same bar, of splitting it into 8 pieces, I've split it into only 2 pieces, and we can see that one of those pieces out of the 2 is the same as the 4 pieces out of the 8. And so 1/2 is the same as 4/8, and this can't be divided any smaller. This is in lowest terms. In B, again, we have 2 bars that are the exact same length, and we need to represent 9/15 in an equivalent form in lowest terms. So I've highlighted 9 of the boxes in the first row, 9 of the 15 boxes, and it also notes for you that instead of splitting this into 15, we could split it into 5 boxes. 1, 2, 3, 4, 5 boxes. In order to have the exact same amount as 9/15, how many fifths do we need? Well, the picture shows quite clearly we have 3/5. And we again can double check our answer. To get from 9 to 3, we divided by 3. To get from 15 to 5, we divided by 3. So 3/5 is equivalent to 9/15, but it's represented in lowest terms. I know it's lowest terms because I can only divide these numbers by themselves and 1. There's no other common factor between these numbers. Whereas I looked at 9 and 15, and I know each of them can be divided by 3. The problem in C gives us a negative rational number, a negative 3 over 12. Well, figuring it out is the exact same. You just need to remember to put a negative in front of your lowest terms form of negative 3 over 12. D might look a little bit tricky to you. In your head, you might be able to say, okay, 2 over 6. I know that the numeric part of that, the value of that, is 1 over 3, but I don't know if it should be positive or negative. Well, for that, we just look at our rules of division and multiplication for positivity and negativity. It looks tricky because the negative is in the denominator. But we remember that whenever we have one negative factor, the final answer is going to be negative. Let's draw out the other possibilities here. We might have a positive number in the numerator and a positive number in the denominator. That's always going to be positive. If we have a negative number in the numerator and a positive number in the denominator, like we saw in question C, there's one negative factor. Our final answer is going to be negative. In this case, we had a positive over a negative. One negative factor results in a negative answer. And the last case we want to look at is if we have a negative number divided by a negative number. Well, now we have two negative factors, which is even, which tells us that we're going to have a positive number. But another way to look at this is that the factor of negative 1 in the numerator and the factor of negative 1 in the denominator can actually cancel each other out, leaving us with a positive quotient. In E, we're given a mixed number, 1 and 1/2. So we've drawn two bars there. We have one completely filled in, and the other one is half filled in. Now we've split both of them into two pieces because the fraction that we're working with is 1 over 2. So it says each bar is going to be split into two pieces. You have one whole and then one piece of that 2. Now, we want to express this as a rational number. That means a fraction using whole numbers. Another way to say that is we want to express this as an improper fraction with just a numerator and a denominator. So what we need to look at is the number of parts that each piece, that each bar is split into. And again, we can tell right from here that it's split into two pieces, and we can see from our picture each bar is split into two pieces. So we know our denominator is 2. What's our numerator? Well, that's the number of parts that we have. 1, 2, 3. And again, we can think of it a little more quickly. We have one whole, which is 2 pieces, and a half of a whole, which is another piece. 3 pieces, 3 halves. Go ahead and do F on your own. F is 2 3/4. The bars are drawn for you there. So you simply need to count the number of pieces that you have out of the total number of bars for each row. Hopefully you were able to refer back to our strategy from E in order to solve F. Just going to show another quick strategy here without the picture. If each bar is split into 4 parts and you have 2 whole bars, then that really means that you have 4 parts times 2. I'm going to multiply those together. That's 8 bars. Now, this 3 tells us that you have another 3 bars. So once we get that 8, we're then going to add 3 more. So that tells us that if we have 2 full bars of 4, that's 8, and we have 3 more, then we have 11 fourths, because each bar is split into fourths. The next thing we need to discuss is the idea that rational numbers, although they are any number that can be expressed as a fraction using whole numbers, they can also be represented in decimal form. Here's an easy example. We have 0.8. Well, we know that the first group of values to the right of our decimal point is called tenths. We could have 1/10, 2/10, 3/10, 4/10, 5/10, etc., all the way up to 10/10. Once we had 10/10, that would just be one whole. Now in this case, we have 8/10. So we're going to write that using words. We have 8-tenths. Which, now that we have that in words, it's really easy to see that that is equal to 8/10. We have something, some whole that's been split into 10 pieces, and we have 8 of them. And again, we want to express our rational numbers always in lowest terms. So think about, how could I reduce this? Well, I know that top and bottom, numerator and denominator, are both divisible by 2. So this reduces to 4/5. Alright, the next one there is a negative number. It's negative 2.51. Think about what that means in words. We want to include our negative sign, so we've got that is going to mean negative 2. And whenever we're using words, this decimal means and. So we have 2 wholes, and we have 51 hundredths. 51 hundredths. So you can think as you go down the decimal places, 1 decimal was tenths, 2 is hundredths, 3 would be thousandths, 4 would be 10,000ths. So we have negative 2 and 51 hundredths, which, I'm going to skip down to my next line, is equal to negative 2, and we're just going to write it exactly as we've said it here, and 51 hundredths. Negative 2 and 51 hundredths. Now that's still not represented as an improper fraction, and so we can find another form for this, and we can use our same strategies as we did before. We have our negative sign still, but we have 2 whole groups of 100, which is 200, and we have 51 more of those parts. So we actually have negative 251 hundredths. Now when we're writing a final answer using rational numbers, and it happens to be a negative answer, then we will usually put the negative sign out front or attach it to the numerator. We'll never leave a solution using rational numbers with a negative sign in the denominator. It's just mathematically, it's ugly, and we don't do it. So we put it out front or we leave it in the numerator. And there you have your notes for rational numbers. We worked with fractions, moving them into lowest form, and we worked with decimals. Your practice problems are found on page 132, numbers 1 through 51. Please come to class with questions.